Okay, so last time we talked about how we establish distances in space over large distances, larger than we can measure via parallax, and how we came to understand in the early part of the 20th century that the Milky Way galaxy was just one galaxy and there were many other galaxies outside of ours, millions or even billions of light years away. And once we made this discovery, again, it didn't happen until 1920 or so, so just barely 100 years ago. Have we understood the actual scope of the universe that we live in, that the Milky Way is not the whole universe. It is just one galaxy, and there are many other galaxies outside of it. Just to review really, really quickly, William Herschel tried to map the Milky Way as best he could in the 1700s, but what he didn't realize is that our view of most of the galaxy is kind of blocked by all the stuff in the galaxy. So the part of the galaxy he was mapping is just our own little neighborhood of the Milky Way. We know that the Milky Way was much bigger than Herschel could have imagined in the 1700s. We talked about the fact that these little fuzzy blobs of light, the nebula that we see in the sky through our telescopes in the 1700s and 1800s, were not understood until our ability to measure the distance to them matured. Now, some nebulas are just clouds. We've seen places where stars form. We've seen planetary nebulas. We've seen supernova remnants. Those are just gas clouds that live right here in the Milky Way. But some of these fuzzy blobs of light we discovered in 1920, or Edwin Hubble discovered in 1920, are actually very, very, very far away. They are themselves made of billions or hundreds of billions of stars, and they are what was called in the 1800s island universes, which is a terrible phrase. We know that the universe means everything, right? So the word galaxy didn't really exist with its modern meaning until we discovered that there were, in fact, other galaxies. So this great debate that happened at the early part of the 20th century was settled by Edwin Hubble. We now know that these spiral nebulae, or some of these spiral nebulae, many of them, are actual other galaxies that can be, again, millions or even billions of light years away from us. What about our own Milky Way galaxy? What is it like? Well, it's hard to know because we're inside of it. And from the inside, it's hard to draw a picture of something because you don't get to see it from the outside. You don't get to get a sort of bird's eye view of this. So any picture you see of the Milky Way galaxy that's not just a bunch of stars across the sky is a drawing, it's a painting, it's an artist's conception. But we do know that there's a central bulge and spiral arms, much like we see in other similar galaxies. We know that it's flatter in one direction, not spherical. It takes the shape of a flattened spiral of some sort. And the distance, well, we'll get to the distance in a second. The spiral arms include a large amount of not just stars and nebula and stuff like that, but dust and gas, just free floating in between the stars. Dust and gas that partly blocks our view of the rest of the galaxy. We saw a couple of times, I showed you a picture of how when we look at one direction of the galaxy, we can actually see this line, this black line that goes across the middle of the galaxy, and that is gas and dust blocking our view of the center. Dimension-wise, the galaxy is a little less than 100,000. This says 90,000. If you want to round off in your brain, the galaxy is about 100,000 light years across, because it doesn't have a hard edge, just like the solar system doesn't have a hard edge. So if you want to kind of hold in your brain a number, about 100,000 light years in diameter. About the size of the central bulge, that the core of the galaxy is about 20,000 light years in diameter. The location of the sun is about 2/3 to 3/4 of the way from the center to the edge. So we're not in the center of the galaxy. We are at the edge. This is also another time in the history of science where we found ourselves, we thought we were in the middle of something, and then we found ourselves off to the side, right? In the old geocentric system, the Earth was in the center and everything went around it. And Copernicus says, nope, sun's in the center and the Earth goes around that. But we did think we were at the center of the galaxy. If you look at Herschel's model of the galaxy, there's a sun is in the center and everything is around the sun. Once we discovered the true scope of the Milky Way, it's like, nope, the center of the galaxy is over here and we orbit around the center of the galaxy. It takes the sun about 250 million years to go around the center of the galaxy once. So all the stars in the galaxy are orbiting around the galaxy's center of mass. The sun's particular orbit takes about 250 million years to go around once. Okay, the distance from the sun to the center of the Milky Way galaxy is about 25,000 light years. So that's about halfway out from the center to the edge. To kind of wrap your brain around what 250 million years is like, that means one orbit ago, if we go back one orbit of the sun around the center of the Milky Way, that is before the dinosaurs evolved. The dinosaurs, remember the extinction of the dinosaurs, we talked about the asteroid or comet that killed the dinosaurs, the Chicxulub impact. That was only 65 million years ago. So this is almost 4 times older than that. Okay, 2 orbits ago was before there was really anything living on the land, just before the Cambrian explosion, just before plants and animals colonized the land. 3 orbits ago, there was nothing. The most complicated creatures on the Earth were sea sponges, barely multicellular organisms. 4 orbits ago, the only thing living on the Earth were single-celled organisms. And 5 orbits ago, the first single-celled organisms that reproduced in some way other than just splitting in 2 evolved. So the Earth has only been around, the Earth and the Sun, our solar system, has only been around the Milky Way about 16 times since the Earth solidified and the Sun started fusing hydrogen into helium. Just like the solar system doesn't stop at Neptune or Pluto, there's the Kuiper belt and there's the Oort cloud of stuff orbiting around the outside. The galaxy doesn't stop at some last star in orbit around the center. We can say, all right, that's the end of the galaxy. There is dust and gas and just random hydrogen atoms that exist beyond that. And there are stars that exist in the outskirts of the galaxy, what's called the galactic halo. So even though most of the stars in the galaxy live in the core and in the spiral arms, there are stars that live out here in the outskirts in the galactic halo as well. Those stars have, just like you think about the Oort cloud of the Kuiper belt, there's stuff like comets that have these highly elliptical orbits, right? They go way in towards the sun, close as Mercury, and then way back out beyond Pluto again. And these orbits take thousands of years. Likewise, there are stars that orbit the galaxy in these giant elliptical orbits. It might take them 1 billion years or 10 billion years or 100 billion years to orbit the galaxy's center even once. Now, what is everything orbiting that's orbiting the galaxy? There's not some object there in the center that everything's orbiting. Well, there's a supermassive black hole in the center, but that's not what everything's orbiting. Everything is orbiting the collective mass of everything else in the galaxy, right? So every star is orbiting around every other star. They're all orbiting around their collective center of mass. How many stars? We don't know the exact number, surprisingly. You might say, shouldn't that be a number that we should know? Well, no, because we can't see the whole galaxy, right? Because there's a bunch of galaxy in the way. So it would be like being in a really, really crowded auditorium with everybody standing up and trying to count everybody in the room, right? You can't see everybody because everybody's all up in your face and in your way. So we don't know how many stars are in the Milky Way. The answer is between 200 billion and 400 billion. And that seems like a huge range probably to you, right? It's always seemed like a huge range to me as well. But last I checked, that's the best we could do. Just like in the solar system, Mercury and Venus go around the sun faster than the Earth, and the Earth goes around faster than Mars, and Mars goes around faster than Jupiter. The orbits of stars around the center of the galaxy are different. And the closer you are to the center, the faster you orbit, the further you are from the center, the slower your orbit. Something else that's different from place to place in the galaxy is the kinds of stars that we find. And understanding this is helped by understanding what we talked about last week and the week before about the HR diagram and how stars evolve. If you look at the the plane of the galaxy, in the spiral arms of the galaxy where we live, you will find stars all up and down the HR diagram, including lots and lots of young, hot, bright OBA type stars. Why? Well, what are OB and A type stars like? They're big and they're massive and they're bright and they burn themselves out fast, which means if there are going to be any OB and A type stars, they have to be being born all the time, right? An O star that was born the same time the sun was born is gone, long gone by now. A B star or an A star that was born when the sun is born is gone. It was gone billions of years ago. It burned itself out. It went supernova. Because the plane of the galaxy, because the spiral arms are filled with gas and dust, there are constantly new stars forming. So there are young, hot, bright O and B stars because there are stars forming all the time. Because there's lots of stuff here to make stars out of, for gravity to pull gas and dust into new stars. We see a lot of these, what's called open clusters, stars that were all born out of the same cloud of gas and dust. The Orion Nebula is going to look like this in another 10 billion years. Right? All those stars are forming in the center of the nebula. Once they heat up, their solar wind will blow all that gas away, leaving behind a bunch of stars that formed in the same area of space. The Pleiades in the constellation Taurus are hot, young, blue, fast-burning stars. Okay, out here in the outskirts of the galaxy, we see very few new, blue, hot-burning, fast-burning, bright stars. What we tend to see are older, dimmer, redder G, K, and M stars. Why? Because there is not enough gas and dust out there in the outskirts of the galaxy for new stars to form. The stars we see out in the halo of the galaxy are often found in these things called globular clusters. These clusters of millions of, well, hundreds of thousands or millions of stars that all formed around the same time, and they are all kind of old main sequence stars, M, K, or G type stars. There's a vocabulary word that astronomers use to refer to these stars. The stars in the plane of the galaxy we call population 1 stars, and the stars out in the galactic halo we call population 2 stars. And one of the things that distinguishes population 1 stars from population 2 stars is something called metallicity. You might remember seeing this as one of the settings that you could set in that stellar revolution simulation we did last week for lab, and I said, don't worry about that. We don't need to set the metallicity, just leave it at the default. What does metallicity mean? It means how many heavy elements, metals and other heavy elements, are present in the atmospheres of these stars. Things like carbon, oxygen, but also things like iron, calcium, magnesium, aluminum, etc. Population 2 stars have very low levels of metals and heavy elements, while population 1 stars have very high levels, well, higher levels of iron and magnesium and aluminum and so on. Why is that? Because population 1 stars are forming in a region of the galaxy where lots of other stars have been born and died and blew up and went supernova, and solar winds spread all of these heavy elements that they've been fusing inside of themselves for billions of years into the galaxy for new stars to form, and they form with those heavy elements from the last generation of stars inside of them. So population 1 stars, which are born and grow up in a place where there have been lots of stars being born and grown up before them, have got the heavy elements in them from the past generations of stars. Population 2 stars are generally as old as the galaxy itself. They formed in a place where there's not a lot of other stars that have formed. There haven't been a bunch of supernovas. There hasn't been the solar wind of planetary nebulas being blown out into space, spreading these heavy elements out into the galaxy. So the stars in the halo tend to be lower in metals because they formed in a less rich chemical environment. Okay, so at some point in the history of the galaxy, we'll talk about galaxy formation very briefly at some point in the next few days. But when the galaxy formed, all of the different kinds of stars in the HR diagram formed everywhere. K, M, A, F, O, B. But the O and B stars in the halo have all burnt out by now. They've all gone supernova. O and B stars do go supernova. They're big and massive, and they're gone. Because there's not that much stuff out in the halo, no new young stars form there. So almost all the stars out in the halo are MK G-type stars. Okay, and in the disk of the galaxy, there are always new, heavy, massive stars being formed. That was only 15 minutes. There's another topic that's related to this. We're talking about the formations of stars out of the leftover junk from the last generation of stars, right? In talking about the galaxy, we talked a lot about stars. We talked some about neutron stars and black holes, the things that stars can wind up as. We talked about what happens when stars die. They can lose their outer layers as a planetary nebula. They can blow up as a supernova. What we haven't talked much about is the stuff in between the stars. So really, really quickly, I'm not going to go through this whole presentation. I'll just say a couple of things about it. I want to talk about this stuff called the interstellar medium. In other words, what's between the stars? Because a galaxy isn't just a couple 100 billion stars. It's all that stuff floating around in between the stars. When we take a picture of the Milky Way galaxy from Earth stretching across the sky, we can see all of this gas and dust blocking our view of the stars beyond it. That stuff is the interstellar medium. We can measure the interstellar medium's presence directly by looking at light passing through this gas and dust. And what we find is that just like on Earth, when you look at the sun when it's low on the horizon during a sunrise, the atmosphere scatters a lot of the blue light, leaving behind light that's red or orange. That's why sunsets look like that. Same thing happens in space. The gas and dust in the interstellar medium scatters more of the blue light, and that leads to a reddening of the light that arrives from distant stars. We can actually look at the light that arrives passing through the interstellar medium and make some estimates of how dense is that interstellar medium, how much stuff is there scattering the light away, reddening the light before it gets to the Earth. What's the answer? Is that what the next slide is? Oh, well, the other thing that happens is it can actually, as the light passes through the interstellar medium, these hydrogen and other elements that live in between the stars, we can take an absorption spectrum and see what the interstellar medium is made out of. Obviously, it's mostly hydrogen because everything is mostly hydrogen, but we can also measure the amounts of other elements present in the interstellar medium. How much stuff is there between the stars? If you just go scoop up some interstellar medium, the answer is not much, right? The average density of the interstellar medium in our galaxy, in the Milky Way, if you go take the Earth and the sun and go to the next star system out, Alpha Centauri and Proxima Centauri, about 4 light years away. Go to the midpoint, halfway between the sun and the nearest star, and scoop up, get a big net. Well, it can't be a net. Get a big box, okay, a 1 meter box, and open it into space and then close it and then bring it back to Earth and see what's inside. You will find that on average, there is about 1 hydrogen atom per cubic meter. So if you go out in space, in interstellar space between the stars, and make a box that's 3 feet by 3 feet by 3 feet, that box will have on average 1 single atom of hydrogen in it, 1 atom per cubic meter. Every once in a while, 1 in 10 boxes will have a helium, 1 in 100 boxes will have something else, an oxygen, a carbon, an iron, a gold. Okay. 1 atom per cubic meter is a very, very, very low density. But space is very, very, very big. There's a lot of 1 meter boxes between here and 4 light years away at Alpha Centauri. We will also find dust. And when we say dust, I mean the stuff we call dust, little tiny mineral particles. Silicates, little chunks of carbon, ices, frozen CO2, frozen nitrogen, and so on. Little bits of iron floating in between the stars. Where do they come from? They are left over from some supernova explosion 8 billion years ago, or they were spit out of the solar wind of some planetary nebula 6 billion years ago. Okay, so the galaxy is filled with junk in between the stars. Okay, this is a picture of what some of that might look like. That's 1 micron across, so a millionth of a meter. Okay, about the size of a piece of dust that might be floating around your house. So even though there's only about an atom per cubic meter of stuff in between the stars, if you take a box that's 100 light years by 100 light years by 100 light years, that box will have a few dozen stars in it. But it'll have very, very many cubic meters of interstellar gas. And even though there's only about 1 atom of gas per cubic meter, it turns out that the mass, if we were to make a box in space, an invisible box, that's 100 light years by 100 light years by 100 light years, and weigh all the stars in that box, a few dozen solar masses worth of stars, and then weigh all the gas in that box, those numbers would be about the same. So even though there's not much stuff in space per cubic meter, right, there's a lot of cubic meters of space in space. So the mass of the stuff between the stars is about equal to the mass of the stuff in the stars, which means if we were to count up all the stars in the Milky Way galaxy, let's say 200 billion stars, there's probably also about 200 billion stars worth of mass, stuff in between the stars. Okay. Which means when we ask ourselves, well, what is the galaxy made out of? We say, oh, it's made of stars. We have to be careful that in between those stars is invisible stuff that we have to keep track of. We can observe it with spectroscopy. We know it's there. We know its composition. And we know that this is the stuff out of which future generations of stars and planets will form. I think I will leave it there, actually. I think I will leave it at there's stuff between the stars. It's mostly hydrogen and helium. Everything's mostly hydrogen and helium. There's not a lot of it per cubic meter, but because there's so many cubic meters of space in space, it adds up to about as much stuff between the stars as there is in the stars. And that's really all you have to know for our purposes about the interstellar medium, the stuff between the stars. Okay, so I will stop it there. And then next video, we'll do just a really quick sort of survey of other types of galaxies other than Milky Way, what they look like, and start to ask ourselves, what are the questions that we want to ask about galaxies? What do we need to know about them in order to kind of piece together our picture of the history of the universe and the evolution of the universe? So that's what's coming next.